Okay, this should be the last review video, so I think I'm covering the last question I was asked about at this point. I'll double check, but I'm pretty sure this is the last one. And I was asked about a question that involved comparing two different oxo acids and how strong the acids were. So real quick reminder of what we're looking at when we look at oxo acids. Basically, when we look at oxo acids, there's really only one thing that we're concerned about, and that is that polarity of the OH bond. There's two things that affect that polarity of the OH bond, and so one of them is the electronegativity of whatever that central atom itself is. The other is how many oxygen atoms are bonded to that central atom. And so when it comes to oxo acids, we don't care how big that atom is because it's not bonded directly to the hydrogen. For binary acids, the size matters. For oxo acids, the size of that atom doesn't really matter because it's not bonded directly to the hydrogen atom. And so what we see is we see two different trends. If we have acids that have the same structure, so basically the same number of oxygens, same number of hydrogens, but it's really just that central atom that's different, then it's really a matter of just looking at, okay, how does this part change? What happens to the electronegativity? The more electronegative that central atom, now this example doesn't look very central, but we could have more oxygens coming off of it, but that heteroatom, the more electronegative it is, the stronger that acid is because it's pulling electrons towards itself and away from this hydrogen that's going to be donated as a proton, essentially. And so when we were comparing things, we compared iodine, bromine, and chlorine. And as the electronegativity of that atom that is not oxygen or hydrogen goes up, you get a stronger and stronger acid. So the chlorine-containing one is stronger than the bromine or the iodine-containing one. If we look at acids that have the same central atom and the same number of OH groups, but different numbers of oxygens, then it's really that number of oxygens that tells us how strong the acid is going to be. And so here, Y is the same in every case, okay? But what we have is we have these extra oxygen atoms that can pull electron density towards themselves, and they can cause basically this proton on the end that's going to get donated to be a little bit more partially positive, and that makes it easier to donate it. And so the more that you have oxygens there, the more that the stronger your acid is going to be. So on to the question I was actually asked about in terms of this content. And so the comparison here is between two acids that are both oxo acids, but they actually have different numbers of protons on them. And so if you look at the HClO4, we have one proton that's going to be attached to an oxygen atom. And we didn't spend a lot of time talking about this. Actually, we didn't really spend any time talking about this in the lecture notes, but this is covered in the chapter. And that is looking at how does this number of hydrogens essentially affect what's going on here. And so if we have only one hydrogen atom, like in the HClO4 situation, there's only one proton that can be donated, okay? But what that ends up meaning is that there are three oxygen atoms over here that don't have their own proton to be pulling away from. And so they're pulling all that electron density essentially away from this hydrogen atom to turn it into that partial positive so that it can be donated. If we look over here in the selenium-containing one, there are two protons that can be donated, but what that means is in each case, we're only left with these two oxygen atoms that are helping to pull towards essentially the center of the molecule. And so you have electron density being pulled this direction, basically, and pulling out from each of these oxygens, but there's only two of them that are helping with that additional pull, if you will. And so it's not quite as effective as what you have when you have three of those oxygen atoms. The other thing to consider in terms of the acid-base strength, or the acid strength, I should say, when comparing these two acids, is that electronegativity of the central atom itself. And so chlorine is more electronegative than selenium. And so what that ends up meaning is that the pull from the chlorine itself is stronger than the pull from the selenium. And so you just have a much stronger acid for that chlorine-containing molecule. I'll be totally honest, I probably will not ask you a question that mixes in this number of protons effect with the electrochemistry effect on the exam itself. It's okay for the quiz, but since I didn't really cover it in the lecture, I'm not going to put that on the quiz, or sorry, on the exam. But the type of thing I could have you compare would be to compare these two acids, right? So these two acids have the exact same structure, right? There's two, I guess I need to put some lone pairs on this sulfuric acid. So there's two oxygens, each of which that have a proton, right? And then we have two oxygens that are helping to pull electron density away from those protons. And so our structure is identical here, right? We have the same number of protons, we have the same number of non-proton containing oxygens. And so really the difference in these two molecules is that central atom. And so if we're trying to compare selenium to sulfur, they're up and down on the periodic table. Sulfur is higher on the periodic table than selenium. And so it has a higher electronegativity, which means that it is going to have a bigger pull of that electron density towards itself, which means these protons on the sulfur containing acid are going to have larger partial positive charges, and it will be easier for them to be donated. And we know that, right? We know sulfuric acid is a strong acid. The first proton comes off completely. The second proton doesn't, but the first proton comes off completely. The selenium acid is not actually on our strong acid list. And so we don't have to, we could make that prediction even without that, but it's really that electronegativity that makes the difference on that difference in the strength of the acids.